Hello, my name is Praharsh Singh and this video is part of the DSP lab experiment number 5. In this experiment I was required to find the DFT of the given signal X and perform some filtering operations and then have the IDFT of the of that function, and then I would be required to compare both the signals, both the filtered and non-filtered signals. So moving on, first we have fs equal to 100. This is basically the sampling frequency, and we have n equal to 256. This is the number of elements in the in the array X, and here we have these n is the number of samples, and w0 real and w0 imaginary are the turtle matrices. They would be having the uh, coefficient defined as e to the power minus j 2 pi by n ij, and first we define theta, so theta is 2 pi by n. Then capital X real and capital X match. These are the matrices which we would be obtaining after we do the DFT on this small x, and x in real and x in image would be the matrices obtained after we perform the IDFT of the signal x real and x image respectively. Now moving on, we will be evaluating the magnitude in the x magnitude matrices and x in magnitude matrices respectively. Now we define the baud rate to be at we set the baud rate as 9600. Uh, Now we will start the DFT of the signal X. So for DFT we know that capital X equal to summation small x times e to the power minus j 2 pi by n nk. So nk would be replaced by aj, and rest 2 pi by n is theta, and so this would be storing the real part of the matrices in the array x real, and the imaginary part of the matrices in the array x imaginary. Then would be taking the magnitude. So magnitude would be the sum of the squares, this variable and this variable, this matrix and this array and this array. So now moving on, so now we have obtained the x real and x imaginary matrices. Now we'll be evaluate doing the filtering on performing the filtering operations on these matrices. So first we have x real we need to filter the matrices as only as most of the information of the would be most of the information of the capital X matrix would be in some particular values for of n. So we would the matrix would be like the function would be somewhat like this, which would decay very fast. So we need to only extract this information. So I found that for I equal to 76 I'm getting an optimum result which performs the filtering operation and also conserves the size of the matrix. So I will be taking the I equal to 76 as the cutoff point. So I'm cutting all the elements which are greater than n equal to 76. So in my x real matrices, x capital X matrix, I would be having only these elements. Then after that, these components basically they die down very fast, and they contain almost no information. So now after since I have performed this operation, then I would be doing the IDFT part. So for IDFT, uh, we have these general equations, x in real and x in image. These are basically the same equations, having the e to the power j 2 pi by n nk expression, and then we'll be having the x in real and x in matched in these two matrices. Mm, Now instead of now while taking IDFT, we'll be doing the conjugate of the W matrix. So here we have not calculated the W matrix, so we have implemented the code directly through two loops. So the conjugate of the two matrix of the W matrix would be given as this, and the and also while taking IDFT we have to take the 1 upon n factor into account. So after each this e loop, then we are doing dividing the elements by n, and thus we would be having x in real and x in match, the DFT, the IDFT version of the capital X matrix, and then we will be calculating its magnitude, and then we'll be out. Then we can now we are ready to compare the signal, input signal, and the filtered signal. We would be leaving the loop void loop part as it is, meaning null with no which basically equals that no loop would be running. And so now uh, we'll be plotting the results. So these are the results. This is my input signal and this is my filtered version. Red one is the filtered version of the input signal. As you can see, this is having a high frequency noise components, and the filtered version is somewhat smoothened out. And this also the red signal contains the same information as the blue signal, as can be seen with the similar shape and the properties of both the waveforms. This concludes my experiment number 5 video presentation. Thank you.